When you see a 3D character rotating in a game or an algorithm predicting stock prices, you are looking at matrices at work. They are the mathematical engines powering modern computing. A matrix is simply an ordered grid of numbers, arranged in specific rows and columns. If that grid is a single row or a single column, we call it a vector. This diagram shows two identically sized matrices being added. You simply add the numbers in the exact same positions to create a new matrix. Scaling follows the same logic. With a single outside scalar, you multiply every number inside the matrix by that value. Adding and scaling are simple element-by-element processes. The complexity of linear algebra begins when you need to multiply two completely separate matrices together. This diagram shows matrix A and matrix B, defined by their row and column dimensions. Before you can multiply them, you have to look at the inner dimensions. Those two inner numbers must be identical, or the calculation is mathematically impossible. Once those inner numbers match, you look at the outer dimensions. These remaining numbers dictate the exact size and shape of your final answer matrix. Checking these dimensions is a mandatory first step. It instantly tells you if a problem can be solved and sets up the framework for the math that follows. This animation shows the row-by-column method. To find the first element of your answer matrix, combine the first row of matrix A with the first column of matrix B. Calculate this by multiplying corresponding numbers and adding the products together. Let's test this. Pause the video and calculate the value for row 2, column 1. To get this answer, multiply the second row of matrix A by the first column of matrix B, adding the products together. Because you are calculating an overlapping dot product, matrix multiplication requires you to think in terms of entire rows and columns sliding together, rather than calculating individual numbers in isolation. This diagram shows some familiar territory on the left. The distributive property you learned in basic algebra still applies perfectly to matrices, but look at the right side. Matrix multiplication is not commutative. If you reverse the order of the matrices, you will get a completely different result. A times B does not equal B times A. Order is absolute in linear algebra. You have to actively suppress the instinct to swap factors around, because moving a matrix to the other side of an equation will break the capulation. In regular arithmetic, multiplying a number by its reciprocal gives you 1. In matrix math, this animation shows the equivalent. Multiplying a matrix by its inverse gives you the identity matrix. This graphic shows identity matrices of different sizes. Notice the pattern. They always have ones running down the main diagonal, from top left to bottom right, with zeros everywhere else. There is a highly counterintuitive rule for inverses. When you take the inverse of two matrices multiplied together, the order of those matrices flips. Because you cannot technically divide by a matrix, the inverse and the identity matrix become your primary tools for isolating variables and solving complex systems of linear equations. To review, matrix addition requires exact dimension matches. Multiplication requires inner matches. Order strictly matters, and the reversal rule flips the order of multiplied inverses. Mastering this specific set of mathematical rules gives you the toolkit needed to manipulate 3D environments, structure data for artificial intelligence, and advance into higher-level linear algebra.